This is Stat 225, and in this video we will be discussing conditional probability and tree diagrams. Conditional probability happens when we have some knowledge of what's happening in the sample space. So if we are looking for the probability that some event B happens, but we know that some other event has happened, so we have some partial information, in this case event A. We can write that as the probability of B vertical line A, where you can read that vertical line as just the word given or knowing. And those are some good keywords to look out for in these types of problems. Another way we can think of this is out of the times that the given or the known event A happens, we're looking at how often event B also happens. And mathematically this is just a fraction. So the probability of B given A is just the probability of the intersection of the two events, B intersection A, divided by the probability of A, which is the given or the known event. And one thing that people mess up all the time, so I really want to point it out, is the given event, the thing that comes after the vertical line, the thing that we know happened, that's what goes on the denominator. Don't get those mixed up. If we switch the order, so we're looking now for the probability of A given B, that means we know that event B has happened, and given that piece of information, I want to find the probability that A happens is the intersection of the two, probability of A intersection B, divided by the probability of the given event, which in this case is B. So keep in mind those numerators in both of these equations are the same. The order of the intersection doesn't matter, but the denominators are very different. So make sure you have the correct denominator that goes along with the given or the known event. When we look at this in a Venn diagram, it's pretty straightforward actually. We just have to think of it a certain way. So if you remember back to our queen and heart examples, we're drawing a card from the deck of cards, and we made a Venn diagram with these two events. Let's say we have some partial information about what has happened. So I draw a card from the deck, and I tell you, hey, the card that I drew was a heart. But I'm not going to tell you the value of the card, I'm just going to tell you the suit. It's hearts. Given that piece of information, I now ask, what's the probability that this card, this heart, is a queen? And so what I'm looking for is the probability of queen given heart. Visually, we can simplify this a lot. If I know the card is a heart, then I don't care about all the non-hearts that are in the deck. I'm only looking at the hearts, and so I can pretend like everything else outside the heart circle is not there. I can zoom in on just the heart circle. And so I can very quickly see from the Venn diagram, okay, of those 13 hearts in the deck, how many of them are queens? Well, one. 1 out of the 13. Let's make sure that lines up with the equation we saw on the last slide. So from the conditional probability equation, we know probability of queen given hearts should be the intersection of those two events divided by the probability of the given event, in this case hearts. We found each of those probabilities in past lectures. That numerator, how many cards in the deck are simultaneously queens and hearts? Well, just one, the queen of hearts, so that's 1 out of 52 in the numerator. And there are 13 hearts in the deck of 52 cards, so 13 out of 52 is the denominator. And we notice that in each of those parts, the 52 cancels, and so we're left with 1 out of 13, the same thing we had from looking at the Venn diagram, or 0.0769. The general multiplication rule is what we get from just rearranging the conditional probability equation. So if you look back at the equation when we had probability of B given A equals probability of the intersection divided by the probability of A, if I just multiply both sides of that equation by the probability of A, I get this. I get that the probability of A intersection B is the probability of A, unconditional, times the probability of B, conditional, or given A. And if I wanted to rearrange this, I could rewrite it using the other equation we looked at for conditional probability, using that A given B equation. Because the numerator in both of those equations from a couple slides ago were the same, I get the same thing here. The probability of A intersection B is the probability of B unconditionally times the probability of A given B. So probability of one event times the probability of the other one given that first one gives me the intersection of the two. And this can be extended for more than two events. If I have three events, A1, A2, and A3, and I want to find the three-way intersection between those three, I pick one of them, in this case probability of A1, find its unconditional probability, multiply that by another one, A2, given that first one, and then I multiply by the last one, given the first two. So I look at the probability A1 happens, then probability of A2 given A1, and then the probability of A3 given A1 and A2. So I'm kind of building this up sequentially, and this works for more than three events. It works for 4 or 5 or 6, but in this class we generally don't go beyond 3. And oftentimes we'll just be using it in the 2 event case. So, quick example of this. If you haven't seen the movie Batman and Robin, it has dialogue that is 75% puns. And 65% of those puns are ice related, thanks to the villain of that movie. We want to know, based on this, what proportion of the film's dialogue in total is ice related puns. So let's first identify the information we've been given so far. So if I just pull a random line of dialogue from the film, the probability that it is a pun is 0.75, based on that first sentence we were given. And then based on the second sentence, what I'm told is a conditional probability. Of the puns, 65% are ice related. So again, remember, if you see the words of or out of or given or knowing, again, we are zooming in on part of our sample space. We're looking at just the puns, so we're conditioning on the puns. So the probability that a piece of dialogue is ice related, given that it's a pun, is 0.65. And what I'm looking for is the proportion of dialogue that is ice related puns. So that means it is a pun and intersection, it is ice related. Using the general multiplication rule, I can find the probability of pun times probability of ice related given pun. Those two pieces of information we've already identified, 0.75 times 0.65, or you can think of it this way, 65% of 75%, because that's really what we're doing when we multiply these proportions together. That tells us that 0.4875 of the film's dialogue is ice-related puns. A very helpful visual when dealing with conditional probability is a tree diagram. And here is a general example. I first start off with an event A and its complement. And I put these letters at the end of a pair of branches to start making my tree. I have unconditional probabilities of each of these things happening. So I have the probability of A, and I can put that on the branch leading to A. And I also have the probability of A complement. I can put that on the branch leading to A complement. I have some other event B, and therefore also its complement. So I add another pair of branches coming off of both A and A complement, with B and B complement at the end of those branches. And now, since these branches are building off of the first set of branches, all the probabilities that go on these branches are going to be conditional. And it's going to be conditional on whatever branch it's coming from originally. So in this very topmost case, I would put the probability of event B given event A, because I'm moving along these branches sequentially. The next one down is going to be the probability of B complement given A. And then I would have the probability of B again, but now given A complement because I'm building off the A complement branch. And finally, B complement given A complement. And this is a completed tree diagram. Obviously, I want to put in numbers for those probabilities if I have them. But this is a very helpful visual when I've been given some unconditional probabilities for one event, and then conditional probabilities for another event given that first one. And you can see the setup here is very useful for employing the general multiplication rule. If we look along the topmost line of branches, I have the probability of A, and then building off of that, I have the probability of B given A. The general multiplication rule says if I multiply those two values together, what I get is the intersection of the two events. Probability of A intersection B. So this is an optional part of the tree diagram, but it's often helpful. You could calculate what that intersection value is and put it off to kind of the right-hand side of the end of those branches. If I then go down one spot, and I've got the probability of B complement given A being built off the A branch, I multiply along that pair of branches, probability of A times the probability of B complement given A, I get the intersection of those two events, the probability of A intersection B complement. And then I can keep going down the rest of the tree. Probability of A complement times the probability of B given A complement gives me the intersection of those two. And then lastly, I have the intersection of the two complements. And what I've done is I've found these four intersection probabilities, and that should cover the entire sample space. Those four values should add up to 1 because I've covered all four scenarios here. We'll first introduce a little bit of new terminology and then do some examples with tree diagrams. Sampling is a big deal in probability and statistics. And when we talk about sampling, it can be done in one of two ways. The first way we can sample is with replacement. So what I do when I'm sampling is I've got a large group of objects or outcomes of a sample space, and I'm pulling them out one at a time. If I sample with replacement, after I've pulled out an outcome, I put it back in, and it can be sampled, it can be selected again and again and again. So any outcome from the sample space can be selected multiple times if I'm sampling with replacement. If I'm sampling without replacement, then once it's out, it's out. Any outcome can only be selected at a maximum of once. So a quick example of this. Let's say you have 6 pens. 4 of them are blue and 2 of them are red. And I'm going to sample 2 of them without replacement. So I've got my 6, I'm going to pull out 1, and then I'm going to leave it out, and from the remaining pens I'm going to pull out another one. I can visualize this entire process, this entire experiment, with a tree diagram. The first thing that happens is I pull out a pen. And so I'm going to denote the possible outcomes, possible events here, as R1 and B1. R1 means the first pen I pulled out was a red pen, and B1 is that the first pen I pulled out is a blue pen. Now, assuming each of the pens are equally likely to be chosen, the probability that I pull out a red pen on the first sampling is 2 out of 6, because there were 2 reds out of the 6 total. And then its complement, pulling out a blue pen on the first try, would be 4/6, because there are 4 blue pens out of the 6 total. Now, whichever pen I pulled out, it's gone. So then, when I look at the secondary branches, in each case, 2 more things could happen. I either pull a red pen on the second try, or I pull a blue pen on the second try. Now, how many pens are there left to choose from? 5. And how many reds are there left if I'm looking at that top set of branches? If I pulled a red out on the first try, there's now only 1 red pen remaining out of the 5 total remaining. And then its complement, 1 minus that, would be 4 out of 5, because there are still the original 4 blue pens in the 5 remaining pens I am sampling from. Now rewind a second. Let's say instead of pulling a red pen out the first time, I pulled a blue pen out. And again, I'm sampling without replacements, so it's staying out. There are still 5 pens remaining, but now in this scenario where a blue was pulled out the first time, there are still the original 2 red pens in there, and only 3 remaining blue pens. So there's a completed tree diagram. From here, I could find all the intersection probabilities. I could list out everything that could possibly happen. So the first thing I could look at is what happens if I pull a red pen out on the first try and a red pen out on the second try. So I'm looking for the intersection of R1 and R2. I get that by just multiplying along the branches, because what I have is an unconditional probability for R1 occurring, that's 2/6, and then that 1/5 is the probability of R2 occurring given that R1 happened. And so I multiply those out and I get the intersection. And I can do this for the other 3 possibilities. Probability of pulling a red pen out and then a blue pen, R1 intersection B2, is just 2/6 times 4/5. A blue first and then a red is 4/6 times 2/5. You'll notice those 2 intersections I just found have the same probability, but they are technically different things. A red and then a blue and then a red. If I don't care about the order, then I could combine these, but when I combine them, I need to add up their probabilities. And we'll discuss more of the idea of when does order matter and when does order not matter in a few videos from now. And then lastly, if I want to find the last probability, what I could do is add up the 3 intersection probabilities I found so far and subtract them from 1, because I'm forming a partition with these intersections. I'm listing out everything that could happen, or I could just multiply along the branches like I have been doing. 4/6 times 3/5 is the probability that I pull out 2 blue pens. And if you want to add up those 4 intersections, you will see they sum up to 1. Alright, let's look at the exact same scenario, except I'm going to change one little thing. Instead of sampling without replacement, I'm going to sample with replacement. So I still have 6 pens, but once I pull the first one out, I'll remember what it was, but then I'll put it back. And so the very first part of my tree diagram, the first pair of branches, is going to look the exact same. There are 6 pens, 2 are red, 4 are blue. Where things start to look different are the secondary branches. So in that topmost case, I'm looking for the probability that I pull a red pen out on the second draw, given that I pulled a red out on the first draw. Well, I pulled out a red on the first, but then I put it back. So originally there were 6 pens to choose from. Now, there are still 6 pens to choose from, and 2 of those are red, and 4 of them are blue. In the second case, I pulled out a blue pen first, but then I put it back. So there are still 2 red pens out of the 6, and 4 blue pens out of the 6. And so my tree diagram here looks a little bit more boring than the last one. And so we notice that, oh, those secondary branches look the same. Each pair looks the same, no matter if I was building off the R1 hub or the B1 hub. So I got 2646, 2646. It's because when I sample with replacement, the original event doesn't really matter. It doesn't have any impact on the probabilities for the secondary event. And that's an idea we'll be talking about in more detail in the next video. I can still multiply along these branches. And so you get R1 intersection R2, probability of getting 2 red pens. I just do 2/6 times 2/6. And I can multiply along the branches to get the other intersections. And again, confirming that those 4 probabilities add up to 1. But you will notice those 4 probabilities are different from the 4 probabilities I had from the last example when I sampled without replacements.